Good morning. I am Sailendra Singh Ojha, Assistant Professor in Department of Electronics and Communication Engineering. Today, we are going to discuss some applications of operational amplifier like instrumentation amplifier, IV and VI converters. So, let us start. Instrumentation amplifier is one kind of IC that is mainly used for the amplification purpose of signals. Conventional amplifiers have some disadvantages like they provide low gain and noise rejection capacity is not up to the mark. So, to overcome these two disadvantages, we prefer instrumentation amplifier. Now, an instrumentation amplifier is used to amplify very low level signal rejecting noise and interference signals, and for the amplification of the signals like heartbeat signals, blood pressure, temperature, earthquakes, and there are various other type of signals. For these signals we can use instrumentation amplifier. And remember that the instrumentation amplifier will have very low signal energy, therefore, instrumentation amplifier should have high gain and should be accurate. They provides high input impedance and low output impedance. Since these amplifiers have high CMRR, so they are generally preferred for the amplification purpose of signal, because they can remove or minimize the noise. These amplifiers have high slew rate also. See, there are various type of circuits used for the instrumentation amplifier, but this is the most popular circuit of instrumentation amplifier. Let us see, analyze this circuit. See, in this case you can see this is one amplifier, this is another amplifier, and there is one more amplifier, that is third amplifier. In this case, amplifier 1A1 is used in the non-inverting mode because we are applying input at the non-inverting terminal. In instrumentation, in amplifier 2 also we are applying input at the non-inverting terminal, and the output of these two given as the input to the third amplifier, and this amplifier is the subtractor amplifier which we have already discussed. This amplifier will provide the amplification of difference of two signals which are applied at these two terminals. So, let us see how does this circuit will behave and how does individual amplifier A1, A2 and A3 will respond. So, before analyzing this circuit, let us see what are the various components which are connected together to form instrumentation amplifier. So, see, in this case R2 resistor is used in the feedback. In this case, for this amplifier A2, R2 is used in the feedback path, and R1 is used here, and R3 and R4 are used for the amplifier A3. This is the simplified version of the previous circuit. Actually, we have connected these two resistors R1 and R1, so it will become 2R1. Rest everything is same. So, if we want to analyze this circuit, then we need to know current and voltage in each and every branch. You know, this is the voltage VI1, this is also the voltage VI1. Why? Because of virtual short circuit. By virtual short circuit concept, the voltage of inverting and non-inverting terminal will be same. So, this voltage will be VI1. Similarly, we have applied VI2 at non-inverting terminal. So, potential of inverting terminal will also be Vi2 and by the concept of virtual short circuit. See, we have one resistor like this, its value is 2R1 and this voltage is Vi1 and this voltage is Vi2. So, the current that will flow through this resistor will be equal to the sum or equal to the difference of the potential or voltage applied across this resistor divided by 2R1. So, current that will pass through this resistor will be equal to Vi2 minus Vi1 divided by 2R1 and Vi2 minus Vi1 is nothing but it is equal to Vid, differential input voltage. So, the current which is flowing in this resistor is Vid upon 2R1. Similarly, same current will flow here because no current will flow inside the operational amplifier due to high input impedance. So, current that is passing through R2 is also Vid upon 2R1. Similarly, the current which is flowing here will also be equal to Vid upon 2R1 because no current will flow here. So, now we know the value of current through both resistors R2. Now, in this way we will try to find out the voltage that will appear here. If I am considering the output of this amplifier as VO1 and output of this amplifier as VO2. So, we will try to find out the difference of VO2 and VO1. So, the simplest way is to apply KVL, Kirchhoff's voltage law, and Kirchhoff's voltage law states that the algebraic sum in a closed loop, algebraic sum of voltages in a closed loop is equal to 0. So, if you will see the voltage drop, I am taking this path. So, voltage drop this across this resistor will be equal to R2 multiplied by Vid upon 2R1 and then plus voltage drop across this resistor will be equal to 2R1 multiplied by Vid upon 2R1, 2R1 multiplied by Vid upon 2R1 plus voltage drop across this resistor which is equal to R2 into Vid upon 2R1 is equal to the voltage that will appear here, that is equal to VO2 minus VO1. So, if you will add these two, it will become R2 Vid upon R1 plus R1 is cancelled with R1 plus Vid. So, if you will take Vid as common, you will get 1 plus R2 upon R1, 1 plus R2 upon R1 or 1 plus 2 R2 upon 2 R1. So, in this way VO2 upon VO1 is equal to 1 plus 2 R2 upon 2 R1 multiplied by Vid. Now, final output voltage, that is output voltage of this amplifier A3. This is what which will appear between these two terminals Vid multiplied by 1 plus 2 R2 upon 2 R1. Now, final output, you know, in case of subtractor amplifier output voltage is equal to R4 upon R3 multiplied by the input. So, you can simply write V naught is equal to R4 upon R3 multiplied by VO2 minus VO1. And do you know VO2 minus VO1 is 1 plus R2 upon R1 into VID. And do you know what is the differential voltage? Differential voltage is VID and differential gain is equal to V naught upon VID. So, it will be equal to R4 upon R3 and 1 plus R2 upon R1. Now, remember, if we will see this, then in this case gain will be more. It will be dependent on R4 and R3 as well as R2 upon R1. So, you have two factors, R4 upon R1 and R4 upon R3, R2 upon R1 and R4 upon R3. So, by properly choosing these values, you can achieve the desired value of gain. This was the generalized case when we have considered R2 and another R2 as equal. If they will not be equal, then you can consider another R2 as R2 dash. Then this gain AD is equal to R4 upon R3 multiplied by 1 plus R2 plus R2 dash upon 2R1, and common mode gain is 0 or it is very small. So, we can say that yes, CMRR for the instrumentation amplifier will be infinite and practically it will be very high. Next is the voltage to current converters. Voltage to current converters are the circuits which can convert a voltage into current, and these type of circuits are known as voltage to current converter. Actually, there are two type of voltage to current converter circuit. One is the floating load voltage to current converter and grounded load voltage to current converter. So, this is the circuit of voltage to current converter, and you can easily see here that we have considered the current which is flowing through this resistor R in this direction and RL in this direction. And remember that you can consider the reverse direction of current also, but if you will consider the current in reverse direction, then other parameters like II and IL will be modified, like particularly in this case it will be equal to V naught minus V in is equal to IL, V naught minus V in upon RL is equal to IL. If you will consider the reverse direction, then IL will be equal to V in minus V naught upon RL. So, it will not affect our analysis whether you will consider the current from left to right or right to left. So, it will not affect the analysis of this circuit. So, let us analyze. This is V in, then by virtual short circuit this current will also be V in. Now, IL will be equal to II and IL is equal to V naught minus V in upon RL is equal to II is equal to V in minus 0 upon R. So, if you will solve this, then you can easily get the value of II and IL, but here our purpose is not to simply solve this circuit, but we really want to find out the value of current in terms of IL. So, we can replace it by IL. So, now if you will write here IL is equal to V naught minus V in upon RL, and in this case IL is equal to V in minus 0 upon IL. So, you can simply say that IL is from this is nothing but this is IL actually. So, if you will simply write, then you will get IL is equal to V in divided by R. Okay. So, in this way you can say that this circuit can convert the voltage into the equivalent current. There is another circuit which is known as voltage to current converter with grounded load. You can simply compare previous circuit and this circuit. In previous case, load was not grounded, but in this case load is grounded. You can see, you can simply check it. So, to analyze this circuit, what we will do, we will apply KCL at this point, and the KCL will say that I1 plus I2 is equal to IL, because this current is 0, incoming currents will be equal to outgoing currents. And we have already considered this voltage as V1. So, I1 will be equal to V in minus V1 upon R plus I2 is V naught minus V in upon R is equal to IL, and IL is equal to V1 minus 0 upon RL. If you will consider all resistance R is equal to RL equal, then you will get V in minus V1 plus V naught minus V in is equal to V1. So, you can simply solve this and you will get I1 is V in minus V1, I2 is V naught minus, it is V1 actually, sorry, it is V1. So, it will also be V1. So, in this way you can solve this circuit. If you will put it, then you will simply get V1 is equal to V in plus V naught minus IL divided by 2. Okay, and it can be simply considered as IL. So, if you will solve it, it is equal to IL and it is divided by R. So, you can simply write V1 is equal to V in plus V naught minus IL divided by 2. Now, we know the value of V1, same value will appear here, and the gain of this amplifier will be 1 plus RF upon R1. So, you can simply multiply this value by 1 plus RF upon R1, and if you will consider both resistances as equal, then 1 plus RF upon R1 will be equal to 2. So, if you will put this value 2 here, that means V naught is equal to twice of V1. If you will put, then 2 and 2 will be cancelled out and you will simply get IL is equal to V in divided by R. So, this is how this circuit can convert voltage into current. These are few applications, like it is used in Zener diode tester, low AC and DC voltmeter, testing LEDs, testing diodes. Now, next is the current to voltage converter. It is a circuit which can convert current into equivalent voltage. This is the circuit. If you will analyze this circuit, then you can say that this II will be equal to this 0 minus V naught upon Rf. So, you can simply write V naught is equal to minus R into II. So, in this way this circuit can convert current into equivalent voltage. This is what which we have to discuss in this lecture. Thank you.